Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we start a new unit on a topic called integrals, and we'll talk a little bit more about that word, what that word means, but that is going to be the big new word for the second half of the semester. So what I actually would like you to do is pause the video and see if you can answer parts A and B on your own. And then come back to the video and join us for a discussion. Okay, so it says the graph below gives the velocity versus time of Jane as she completes her morning run. Use it to answer the following questions. First one being, see if you can figure out how far Jane ran total. And the second, well, we'll get to the second one in a second. So her velocity, right, is given by the y-axis, and because we have a horizontal line, that means her velocity is constant for the entire run. So it doesn't change. She starts off running at 8 miles per hour, and she finishes running at 8 miles per hour. And it looks like she runs for 1.2 hours total. Well, if she's running 8 miles per hour for 1.2 hours total, right, we should just be able to do a little multiplication, right? 8 miles per hour times 1.2 hours. We could actually pay attention to our units here because they are going to simplify. But number-wise, we get 9.6. And if we think about what's going on with our units, well, we have miles per hour times hours, which means our hours are going to simplify, and we're left with 9.6 miles. So, course of her run, she ran 9.6 miles. This one was pretty straightforward, again, because our velocity was constant, it wasn't changing. Part B says, look at the area under the graph. And when I say under the graph, I mean between the function and the x-axis. And what do we notice? Well, let's take a look at that area. So we're talking about this area right here. Box that off. So all this area. Well, this is the area of a rectangle, right, which is pretty easy to find. Our length is 1.2. Our height is 8, which means our area is, again, not equals, 9.6. And if we look at units, it would be miles if we looked at the units of the length and the height like we did for part A. So this is your first introduction to a big idea in this unit. Area under a curve, or area between the function and the x-axis for a velocity function, will tell us something about the total distance, displacement, or net distance. I'm not going to tell you exactly which one that is right now, right? But it has a connection with at least one of those. Let's move on to another one and see if we can apply this concept again. So here we have another velocity time graph. It says the graph below represents the Johnsons' road trip across the state of Tennessee. So using the method we used in part B for number 1, can we figure out the total amount of miles they traveled during their trip? So again, sort of a different example because it's not a constant velocity the entire time, but see if you could figure out how to maybe break this down to figure out the total amount of miles they traveled. Well, just like up above in part B, where we were finding the area, we can do the same thing here. We just need to break this into shapes that we can find the area of. And there's a couple different ways you could break it down, right? Depending on whether you remember the formula for area of trapezoids, etc. But I'm going to break it down into those 4 shapes. So we'll call this 1, 2, 3, and 4. And if I can find the area under all 4 of those, I can just sum them together to get the total area. Well, the area of 1, that's just going to be a triangle, right? So 1/2 times the base, which is 1 times the height, which is 60. Make sure we pay attention to those units on the y-axis. So that gives us 30. If I look to find number 2, that is a rectangle. So we have a length of 3 going from 1 to 4 on the x-axis, a width or a height of 60. So that gives us 180. Area of number 3, this is a trapezoid, so it's equal to 1/2 times the sum of the bases being the parallel sides. So if I look at the parallel sides, let me do a different color here. That would be this length right here. So one of them is 60. The other one is just 50. So I have 60 plus 50. And then you have to multiply by the distance between the bases, which in this case would be on the x-axis. So this distance right here, which is 3. So if I multiply all of that together, that ends up giving me 165. And I have one more trapezoid for number 4. This time my two bases are the horizontal. This time my two bases are the horizontal segments. So we're going to have 1/2 times a quantity of 3 plus 2. And then the distance between the bases, or the height of the trapezoid, is, what is going on? Is 50. So if I multiply those together, that gives me 125. And then if I want to find the total area, the total area, which represents in this case the total amount of miles they traveled, I'm just going to sum these all together, and that ends up giving me 500 total miles that they traveled. So both of the examples we've looked at currently have been when the function is completely positive over the interval we've been looking at. And when it's completely positive, we're able to figure out the total distance that the person has traveled, or biked, or ran, etc. Let's now take a look at what happens when the function dips below the x-axis over our interval. So here we have another velocity graph. This represents a mouse's velocity as they move through a maze. And we're asked to find the total displacement. So remember, displacement's different from distance. Displacement can be positive or negative. Displacement is just how far did you end up from your starting point. But that number can be positive or negative. So you may want to pause the video and think back to the differences between total distance, net distance, and displacement. But total and net distance, those both have to be positive. Displacement can be positive or negative depending on your direction from where you started. A couple things to think about. There are zeros on this graph at 6 and 12.5. I know it may not look like the zeros right at 6, but I'm doing that for simplicity's sake. So again, we need to break this up into different figures that we can easily find the area of, and then do some adding at the end to figure out the displacement. The only difference is, again, this graph is partly below the x-axis, which may change, how we look at some of these areas. So let's jump right in. This first figure will be that triangle. The second figure will be the trapezoid right there. The third will be this triangle, and the fourth will be this trapezoid. So I still have 4 figures to find the area of. Let's start with number 1. The area of 1 is equal to 1/2 times the base. Be careful, the base is not 6 here, it's 4. I actually made that mistake when I first did this video. We're not counting this, right, because his velocity there is just 0 meters per second. So the mouse is not moving at all over the first 2 seconds. So basis 4, the height is 3, so I end up getting 6. Now, we have to think about this, right? This 6 represents an area that's below the x-axis. So if the velocity graph is below the x-axis, what does that mean about the direction that the mouse is traveling? Well, it means the mouse is traveling in the negative direction, right? So if we just think about left and right, the mouse is traveling to the left. So even though areas in geometry are never going to be negative, we have to think about this area or this quantity being negative because it represents it represents the mouse moving in a different direction than if it was positive. So this 6 is going to be negative, and that's going to help us understand at the end which direction the mouse was going. The area of the second figure, which is a trapezoid, so we have 1/2 times one of the bases. The top base here is 5, bottom base here is 6.5. So we have 5 plus 6.5 times the height, which is 2. That ends up just giving us 11.5. And we'll keep that positive because it was above the x-axis. The area of 3 is that triangle right there. We have 1/2 times the base, which is 3, times the height, which is 4. And again, this area is beneath the x-axis. So we're going to put a negative sign there to let us know that the mouse was moving in the negative direction over that time. In the area of 4, that is another trapezoid. Actually, the two bases here are the same as the other trapezoid. We have 6.5 here, and we have 5 if we look at that length right there. And the height is also the same, that is 2. So we get another area of 11.5. Again, this was beneath the x-axis though, so we're going to make that area negative. So I know it's asking us for displacement. I'm actually going to go through all 3 of them. I'm going to go through total distance, net distance, and displacement just to help you understand, how we use these negatives. If I'm looking at total distance, I actually would not want to use the negatives, right? So total distance is going to be the absolute value of all these areas. The area or the distance that the mouse has traveled over our first interval, right, which was represented by this triangle. Well, the mouse traveled 6 meters. They just did it in the negative direction, but they still traveled 6 meters, right? In our second interval, the mouse traveled 11.5 meters in the positive direction. In the third interval, and I know the third and the fourth intervals kind of overlap, but in that third area that we found, the mouse traveled 6 meters in the negative direction, but it's still 6 meters total. And then in the fourth area, we found the mouse traveled 11.5 meters, again in the negative direction, but still 11.5 meters nonetheless. So if I wanted to find the total distance, I would just be adding up all the positive versions of these numbers. So positive 6, positive 11.5, positive 6, and positive 11.5 again. This would end up giving me 35 meters. So the total distance the mouse travels is 35. Let's do displacement next. Because remember, displacement and net distance are very, very closely related. Displacement would just be when we add these up given the signs we found for them. So again, because displacement needs a positive versus negative sign, whereas distance is always positive, well, we're going to factor in the negatives for displacement. So if we add all these up, we get negative 12 meters for displacement. And that just means the mouse ended up 12 meters in the negative direction from where it started. Now, net distance, well, that's just the absolute value of displacement. So the net distance the mouse travels is just 12 meters. So depending on what you're trying to find, whether it be total distance, displacement, or net distance, that'll let you know whether you need to factor in those negative signs for the areas or not. All right, let's see what's next. I think we kind of already discussed the differences between the mouse problem and the other two problems. The mouse problem, the function dipped below the x-axis. So our areas, some of those ended up being negative, which made our total, net, and displacement, those were different values. Part C, we've also talked about. In a velocity versus time graph, what does the area under the function represent when it's below the x-axis? Well, when the function is completely above the x-axis, it just represents total distance. When it's above the x-axis, total distance and net distance are both going to be the same. If the function ever dips below the x-axis, though, well, all of a sudden, the area represents displacement. And actually, let me just reiterate one more thing from up above. When the function is completely above the x-axis, actually all three are the same. Not just net and total distance, but net distance, total distance, and displacement. Those are all going to be the same. When the function crosses the x-axis, when it's both positive and negative, or maybe just negative, well then the total area that you get, that's going to represent the displacement. And then if you wanted to find the net distance, right, you could take the absolute value of displacement. If you wanted to find the total distance, you'd have to go back and make each of those individual areas positive. Last thing to talk about is this function down here. Again, it's a velocity function, but it looks a little different from the ones above, right? So see if you could figure out the total distance the car travels from 0 to 2 hours. Again, that would just be the area under this function because it's completely above the x-axis. So you don't have to worry about negative areas. Well, this one's, much more difficult, right? Because there's a curve rather than segments, which the graph is made up of. So if you were trying to break this up into shapes, right, you could. Like this shape is pretty close to a triangle, but it's not a triangle, right? Because the hypotenuse is curved, right? Same thing if you, tried to break the rest of this up, right? This piece right here, almost a trapezoid, but this piece up top is not straight, it's curved. So same thing, you could break this up and get a good estimate, which is something we'll be doing in later lessons actually. So you could break this up into triangles, trapezoids, etc. to get an estimate of the area under the curve or under the function, but it's not going to be an exact area. So this is where the calculus part comes into play. Up until this point in the lesson, everything we've done, you could have probably done, after geometry, or maybe even sooner. Now, though, when we have a function that's curved, rather than made up of straight segments, we need another method. And that's what we're going to get into basically for the rest of the year, is talking about this idea of integration. So just to give you a small taste of what that's going to look like, if I wanted to figure out the area underneath this curve, so this area right here, well, I would need to know how to evaluate this expression here. this right here, this is called an integral expression. And once you know how to evaluate something like this, you will be able to figure out the area under any type of curve, whether it's made up of straight segments or whether it's made up of curved segments. So that's where I'm going to leave you today. I look forward to seeing you next time where we dive more into this topic.